Hi guys, this is Jonathan Lambert with the Mathematics Development and Support Service at National College of Ireland, and this short video, our first video in our series of videos dealing with functions, is going to attempt to define what a function is. And the way we're going to do that, or the approach that we're going to take in this particular video, first of all, is to define a function from the perspective of a relation. Now I've got a whole set of videos up online, up on YouTube with respect to what relations are, but maybe let's just have a quick look at a relation again. Yeah, okay. So what we'll do is we'll define what a relation is, and then we'll put a restriction on them relations, and what we'll end up with is what we're going to call a function. Okay, I'm going to do it from this perspective first of all, and then what we'll do is in our next video we'll do it from another perspective, which is where we define it a little bit more rigorously. Okay, so let's just recall. Okay, recall a relation, okay, a relation, okay, a relation or on a set A, okay, is simply a subset. It's a subset of A cross A, okay. So that's what we define a relation to be. It's a subset of A cross A. Okay. Now it doesn't have to be the same set. We could have A cross B where B is different to A. Okay. But basically any subset of a cross product, okay, is what's defined to be a relation. So maybe we should actually do that now. Yeah. So given two sets, two non-empty sets, let's say, two non-empty sets, okay, A and B, okay, where A and B are not necessarily the same, okay. So given two non-empty sets A and B, we say that R is a relation. It's a relation, okay, on or on A cross B, okay, if R is a subset, okay, of A cross B. Okay. So what the hell do I mean here? Okay. Well, let's just define two sets. Okay. Let's say let A equal the set 1, 2, 4, and let's say let B equal the set, let's say 2, 3, 4, 7. Okay. Well then, R is a subset of A cross B. Any subset of A cross B, okay, is defined to be a relation. So let's construct A cross B first of all. Okay, so let's construct A cross B. And the way we're going to do that is we're just going to create a table. The table is going to look something like this. Okay. We're going to list the values of A down in the first column. So the values of A are 1, 2, and 4. And we're going to list the values of B across the first row. So the values of B are 2, 3, 4, and 7. And we're going to construct the ordered pairs, where the first element of the ordered pair comes from this first column, and the second element in the ordered pair comes from the first row. So we have 1 is related to 2, so 1, 2. We have 1 is related to 3, so 1, 3. 1 is related to 4, so that gives us 1, 4. 1 is related to 7, so that gives us 1, 7. We have 2 is related. We have 2 is related to 2. We have 2 is related to 3. We have 2 is related to 4. We have 2 is related to 7. We have 4 is related to 2. We have 4 is related to 3. We have 4 is related to 4. And we have 4 is related to 7. Okay. Now in this particular construction, in previous examples when we constructed relations, we constructed them on a single set A. Okay. In this case here we're going to have two sets A and B, not necessarily the same, but we still construct the cross product. Okay. So actually in this situation here, A cross B is the set, okay, it's the set of ordered pairs that we've constructed here. So it's the set 1, 1, 1, 3, or it's the set that contains the ordered pair 1, 1, the ordered pair 1, 3, the ordered pair 1, 4, the ordered pair 1, 7, the ordered pair 2, 2, the ordered pair, let's say the ordered pair 2, 3, the ordered pair 2, 4, the ordered pair 2, 7, 2, 7, the ordered pair 4, 2, okay, the ordered pair 4, 3, the ordered pair 4, 4, and the ordered pair for 7. Okay, so what we have here is we have a cross product. Okay, so what we know is that a relation is any subset of that particular cross product. Okay, so we could take any subset of that particular cross product and we could construct a relation. Okay, by definition, a relation is a subset of a cross product. Okay, but I suppose how many relations could we construct? How many relations can we construct? Can we construct? Well, actually, another way of actually saying that is how many subsets? How many subsets? How many subsets can we create? Can we create? Okay. How many subsets can we create? Okay. That's, I suppose, a question. Yeah. Okay. Well, we know that the power set. Okay. That the power set. Okay, is the set of all subsets. Okay, so the power set would be the set of all possible subsets from this particular cross product. Okay, and we know that the cardinality, okay, of the power set, that the cardinality of the power set is defined to be, well, the cardinality of the power set of a set, now the set we're interested in is A cross B, of A cross B, the cardinality is simply equal to 2 to the power of the cardinality of the set that we're constructing the cross product from. So it's equal to 2 to the power of the cardinality of A cross B. Now in our situation here, this is 2 to the power of, well, how many ordered pairs have we got? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So it's equal to 2 to the power of 12, which gives us a value of, let's do that on our calculator. So we have 2 raised to the power of 12 gives us a value of 4,096. So there's 4,096 possible subsets that we could create from this particular cross product. And every single one of them subsets are relations. So all of them subsets are by definition relations because they're a subset of that particular cross product. Now, we're only interested in certain types of relations, okay? And these certain types of relations from this particular cross product we're going to call functions, okay? So how the hell are we going to create them particular functions? So what is a function, okay? So I need to probably give you a definition now of what a function is, okay? So a definition of a function, so let's say the definition of a function, okay? Well, to create a function, I need to have a subset of some sort of cross product. And to have the cross product, I need to have the two sets that the cross product is built from initially. Okay. So what I'm going to say here is this: is let A and B. So we're going to say let A and B be non-empty, empty sets. Okay. So let A and B be non-empty sets. Okay, and let F be a relation, okay, be a relation from A into B, okay, so from A into B. Really what I'm saying here is this, is that F is a subset of A cross B, okay, so let's just keep that in mind, that's what I'm really saying, okay. So let A and B be non-empty sets, and let F be a relation from A into B, okay. Well then, okay, so then, okay, so let's think about it. Then we say that F is a function. Okay, it's a function. Okay, from A into B, from A into B. Okay, if the following two conditions hold. Okay, so if the domain of F, if the domain of F is A, okay, and the way we symbolize that is that the domain of F equals A. That's one restriction, okay, and two, okay, and what we're also saying, and for all ordered pairs, okay, so for all ordered pairs, so for all A's and B's, and let's say C's and D's that are elements of F, so for all ordered pairs that are in F, okay, if A is equal to C, well then we must have that B is equal to D, that B equals D. Okay. Now we'll get to this particular what this actually really means now in a few moments. Okay. But all it's really saying is that if you have two ordered pairs where the first entry in the first order pair is the same as the second entry in the second order pair, okay, if we do have that situation, well then what we must have the second entry in the first order pair being equal to the second entry in the second order pair. Okay. Now from a graph perspective, that's putting a particular type of restriction on our sets, if that makes sense. So this is our abstract definition. This is our abstract definition of what a function is. Okay. So let's have a look at some examples. So let's have a look at some examples, if that makes sense. Okay, some examples. Okay, so what we're going to do is we're just going to choose some examples, and we're going to just see how we get on with those particular examples. Okay, so let's choose some examples. Okay, so what we'll say is, okay, we'll still use the set that we had earlier on. Okay, so let A equal the set 1, 2, 4, and B equal the set 2, 3, 4, and 7. Okay, so we're going to have two sets A and B, and let's say that F is a relation from A into B. Okay, so let A be that set and B be this other set, and let F be a relation, okay, from A into B. Okay, so it's a relation from A into B, and let's have a look at what this particular F might look like. Okay, so what I'm going to do is I'm just going to create a set here, the set A. Okay, so we have the set A. The set A contains the values 1, 2, and 4. Okay, and I'm going to say that the set B. So this is the set A. Okay, and the set B contains the values. So here's the set B. Contains the values 2, 3, 4, and 7. Okay, and what I'm going to do is I'm just going to do some mappings. It's just a relation. Okay, so 1 is associated with 2. Okay, that's brilliant. 2 is associated with 3, and let's say for argument 4 is associated with 7. Okay, so there's a particular relation. If you want to write it down, this relation F is the set that contains the ordered pairs 1 is taken to 2, 2 is taken to 3, and we have the ordered pair 4 is taken to 7. Okay, so this is this particular relation F. It's simply, when I'm using the letter F, it doesn't matter what we're using. It is a relation because it is a subset. Okay, this F here is a subset of A cross B. Okay, you can see that 1, 2. Where's 1, 2? Have I missed 1, 2 here? Oh, I defined them differently here. Okay, so if you think about it here, we have the cross product of A with B is 1 goes to 2, 1 goes to 3, 1 goes to 4, 1 goes to 7, 2 goes to 2, 2 goes to 3, 2 goes to 4, 2 goes to 7, 4 goes to 2, 4 goes to 3, 4 goes to 4, and 4 goes to 7. So this is a subset of A cross B, right? This is a subset of A cross B, and hence it is a relation. Okay. Now, with respect to this particular relation, let's check these two properties. Okay. So it's a relation from A into B. Okay. So is the domain of F equal to A? Okay. Now A contains the values 1, 2, and 4. Okay. So is the domain are basically the first values in our ordered pairs. Okay. So the domain values are going to be this 1 here, this 2 here, and this 4 here. So our domain is the values 1, 2, and 4. Okay. Now the question is 1, 2, and 4 the same as A? Okay. In this case, it is. This is equal to A. It's equal to 1, 2, and 4. So we match the first condition here. So when we defined F to be a relation from A into B, okay, the set A contained the values 1, 2, and 4. Okay. Well then, for F to be a function, or to be one step closer to being a function, the domain values of F, okay, 1, 2, and 4, must be the same as A. In other words, what we're saying here is this: for something to be a function from one set into another, okay, every value in this particular set here, this particular set A, needs to be mapped into some value in B. Okay, that's really important. Okay. Now, the next condition says that for all ordered pairs, okay, for all ordered pairs that are in F, in other words, for every single one of these ordered pairs, when I take any two of them, okay, if the first value in the first ordered pair that I choose is the same as the second value it's the same as the first value in the second one, okay, and you can actually see that no ordered pairs, well, I suppose I could map, if I take any two ordered pairs, I could select one with 2 and one with 2, okay, if that makes sense, okay. I could select one with 2 and one with 2, okay. Now, in this particular situation, the first ordered pair, we have a 1. The 1 here is the same as the 1 here, okay, so I have this. But then what we need to have is, what must hold, yeah, is that the second value to the second value must be the same. And in this case here, we have the second value goes into the second value is the same, okay. So at this stage here, we're one step closer to this being a function, okay. What about 1, 2? We could also pair 1, 2 off with 2, 3, okay. So 1, 2 could get paired off with 2, 3, okay. They would be two possible ordered pairs that I could choose from the relation, okay. Now it just says if A is equal to C. In other words, if the first value here is equal to the second value, to the first value here, okay, this value compared to this value, if they are the same, well then this value must be equal to that value there. But look, the first value and the second value aren't the same, so I don't need to check the condition that the second values that they're mapped into are the same. So we can ignore that. The other possibility is that we could have 1, 2, we could choose the first order pair 1, 2, and the second order pair 4, 7, okay? In which case, let me just maybe go to another page here, okay? Let me go to another page, okay? Okay, so I'm just trying to define this concept of what a function actually is, okay? So let's just go to another page here. I could choose the order pair 1, 2, it's associated with the order pair 4, 7, but look, I don't need to check the second condition. I don't need to check the second condition because I only need to check the second condition if the first values in both order pairs are the same. Okay. Now in this particular situation here, the first values in these order pairs, the first values here are not equal, so I don't need to check. I don't need to check to see whether these values here are equal. Okay, so I can ignore that particular situation. What else could we have? We could have 2 to 3. We could have 2 with 3, and we could have 1 with 2. Okay. Well, once again, they're not the same. Whoops, they're not the same. They're not equal. So I can ignore this particular condition here. So I can ignore. Okay. What else have we got? We have 2 to 3 with 2 to 3. Okay. Well, they're the same here. So I need to check they are equal. So I need to check the second condition. Okay. That these two things are equal, which they are. So that's good. That's good. Okay. And we continue in this particular fashion. But I suppose the important thing about a function is this, yeah? A function, really what it's saying is this, is that a function from A into B, okay, must map every value in A, and must map every value in A into some value in B. That's what the first condition is saying, okay? And then the second condition is saying this, is the second condition, okay, the second condition, okay, the second condition, okay, is saying something like this, okay? That if we have situations like, let's say, we have something like 1, 2, 4 being mapped into 2, 3, 4, 7. Well, let's map everything in. So we have 1 goes to 2, we have 2 goes to 3, okay, and we have 4 goes to 3, okay. Here's a mapping here, okay. Let's check this function out. Well, first of all, it meets the first condition. It meets if this is set A and this is set B, okay. It satisfies the first condition. Every value in A, okay, every value in A, okay, is mapped, okay, if that makes sense. Every value in A is mapped into some other value in B. Okay, that's good. So we match the first condition. What about the second condition? Well, let's have a look. Let's have a look at the ordered pair 2 goes to 3. So we have 2 goes to 3. And we have the ordered pair 4 goes to 3. Okay, so we have the ordered pair 2 goes to 3, and we have the ordered pair 4 goes to 3. Okay, so what about this as another example here? Okay, well, we don't need to worry about the second condition because these two values are not equal. Okay, we only need to worry about the second condition if these two values are the same. Okay, so in this situation here, we have every single value is mapped into some other value. Okay, every value in A is mapped into some other value in A. Okay, and we don't have a situation where we have two values. Okay, we don't have a situation where we have a value in A going to two separate values. For example, let's say for example. Okay, so for example, okay, let's consider the mapping 1, 2, 4, and let's say it's mapped into 2, 3, 4, 7. This is our A and our B. Okay, so we have 1 is mapped to 2, we have 2 is mapped to 3, and we have 4 is mapped to 7. Okay, at this stage here, this is definitely a function because we have every value of, well, we have the first condition is met. Every value over here is mapped into some other value over here. But let's do something else. Let's say we have 1 is also mapped into 3. Okay, so now what we have is this, is that we have the ordered pair 1 is mapped to 2, 1 is mapped to 2, and we also have the ordered pair 1 is mapped to 3. Okay, now these two things here are the same. These are equal. So because they're equal, we need to check the second condition. Okay, because the A is equal to the C, we need to check the second condition and make sure what must hold is then the second values must be equal. Okay, but in this situation here, we have that the 2 is mapped into the 3, that these are not equal, so this is not a function. Okay, so this is not a function. Okay, so this thing up here ain't a function, if that makes sense. Okay, because we have, in this situation, you can sort of see it here. Maybe if I get another pen, get a red pen. Okay, we have, there's a line coming out here, and there's a line coming out here, going to different values from the same value. Okay, so what we mean by a function, we mean that a function maps every value in this set here. Okay, it maps every value into some other value over here, but what we never have is we never have two arrows leaving a single value over here going to different values over here. Okay, now I'm just going to finish up now in a moment because I want to define what we mean by the domain. I want to define what we mean by the codomain and what we mean by the range. Okay, so let's have a look at some examples. Okay, so I'm going to have 3 examples here. Okay, 3 examples, okay, of mappings. Okay, 3 examples of mappings. The set here is 1, 2, 4, 1, 2, 4, 1, 2, 4, and the set over here is 2, 3, 4, 7. The set over here is 2, 3, 4, 7, and 2, 3, 4, 7. This is A, this is B, this is A, this is B, this is A, this is B. Okay, and what I'm going to say is that F, we're going to consider 3 functions. We're going to, well, 3 relations: F, G, and H. Okay, so let's have a look at F. Okay, so F is a relation. It takes 1 to 2. It takes 2 to 3. Okay, and that's all we have. So F is a relation on A cross B, or is a relation from A into B. Okay, so it is a relation, if that makes sense. There is a relation from A into B. Okay, because we have values from A going into values for B. Okay, but is it a function? Well, we're defining F to be a relation from A into B. So when we consider this A, every value in A must be mapped into B. And we don't have every value. Okay, we have an example here of a value here that's not mapped here. So F is not a function. Okay, if that makes sense. Okay, F is not a function from A into B. Okay, now F would be a function. F would be a function. Okay, F would be a function. Let's say I'll do a little small set. Okay, F would be a function if this set was 1 and this was 2, and if this set was 2, 3, 4, and 7. 1 is taken to 2 and 2 is taken to 3. Let's say this is the set A prime and this is still the set B. Okay, if F was defined on this, we have every value in A prime is taken to a value in B. Okay, so this would be an example of a function. Yeah. Okay, that's a good example there. Okay, let's look at G. Okay, in the relation to G, what we have is we have 1 is taken to 2. Okay, we have 2 is taken to 3, and we have 4 is taken to 7. Okay, so G, is G a function? Don't forget we've got two conditions. The first condition is that is G a function from A into B? The first condition is that every value in A must be mapped into some value in B. So that's good. Okay, so we have, well, first of all, G is a relation. It is a relation from A into B. That's the first thing that we notice. There is a relation, but is it a function? Well, one, every value in A is mapped into B. Really what I'm saying here is that the domain of G is equal to A. Okay, so once the domain of G is equal to A, okay, well then that meets our first condition. What about the second condition? Okay, the second condition says that we should never have any double arrows leaving domain values. We should never have any double arrows leaving domain values. Okay, well, in this case here, we don't have any double arrows leaving domain values and going into separate values over here. So in this case here is there we cannot find a situation okay, where we have an A and B, and we have an A prime and a B prime, okay, that are elements of F, and A is equal to B, okay. We can't find any of these things, any of these ordered pairs, okay, where A is equal to B, and we have B is not equal to B prime. Okay, we can't find any of them. Okay, we can't find any situations where we have the first value in our first order pair is, oh, that should be A prime here. A prime is equal to the second value in our second order is equal to the first value in our second order pair. We have none of them situations, yeah, okay, and that they're mapped into different values. We don't have them there. So this is a function. So in this case here, G is a function, okay. And then finally, let's have a look at another situation. Okay, in this case here, we have 1 is taken to 2, 2 is taken to 3, 4 is taken to 4, and we have 2 is taken to 7. Okay, I suppose the first thing here is this: is that the first condition is satisfied. Okay, every value in A is mapped to a value in B. Okay, so our first condition is satisfied for H. Every value in A is mapped into B. That's good. Okay, but the second condition is not satisfied because we have a situation where we have a double arrow. We have a mapping going from here to here. We have a mapping going from here to here. Okay, let's have a look at them two things. What they are: 2 is taken to 3. 2 is taken to 3, and we have 2 is taken to 7, and we have 2 is taken to 7. So these two things here are the same. These are equal, okay? So we have the A is equal to the A prime, okay? But what we have is we have these two things here are not equal. They're not equal. So we have a situation where we have a double arrow leaving a single domain value, okay? So in this case here, we have H is not a function, okay? Right. Just something else to keep in mind, okay, is that the values that are actually mapped from a set into another set, okay, we call the domain. So if you want to construct a function, all you have to do to calculate its domain is to take the values that are actually mapped, okay. They're mapped into specific values over here, okay. The whole set that they could go into, the whole set, is what's known as the codomain. So that black circle here where all them values is known as the codomain. This black circle here where all the values is known as the codomain, okay. This black circle here where all the values is known as the codomain. Okay. Now, the actual values that are mapped into, in this case we have these here, we have these things here, okay, and we have everything here, okay. That the actual values that the mapping maps into Okay, these are known as the range values. These are the range values, and these are the range values here. And it just happens in this situation here that the range is equal to the codomain. But it's not always the case. It's not always the case that the range is equal to the codomain for us to have a particular function, if that makes sense. Okay. So let me give you an example of that, and then maybe we can actually finish up here. Okay. This is quite a long video. Okay. So maybe what we'll do is we'll just have a look at another example. Okay, let A equal the set 1, 2, and 4, and B equal the set. What did I say it was? It was 2, 3, 4, and 7. 2, 3, 4, and 7, and let I, okay, be a relation. Okay, from A into B. Okay, so what that means is that I takes values from A into values from B. The values of A are 1, 2, and 4. The values of B are 2, 3, 4, and 7. Okay, so I is a relation, so it takes values from here into here. So what we'll have is maybe 1 is taken to 2, we'll have 2 is taken to 7, and we'll have 4 is taken to 3 as an example. Okay. Condition 1 is satisfied. Okay, condition 1 is satisfied because the domain of I, okay, the values that are actually mapped out of this set into here is all the values is equal to A. So the first condition is satisfied. What about the second condition? Okay, the second condition is also satisfied. Yeah, so condition 2 is satisfied. Yeah, okay, because there are no double edges, okay, double edges leaving a single point, okay, and going to separate points. Okay, so we can't find any of them, so this is a well-defined function. So this is a function. So I is a function. Okay, so I is a function, okay, by definition. Okay, but what we also have here is that we can see that in this situation here, okay, we can see the codomain is in black and the range is in. So the codomain is in black and the range is in red, and the range of the values are in red, if that makes sense. So here's an example of a valid function. Okay, but in this situation we have the range is a smaller set than the codomain. Okay, doesn't have to be. Okay, the last example that I gave over here was actually, well, we broke it. Okay, here was another example of a function here. Okay, so if we have a function, if you think about it, okay, if we have a function where the range is equal to the codomain, if the range is equal to the codomain, okay, let's think about that. If the cardinality of the range, okay, equals the cardinality of the codomain, okay, if that's true for a function, okay, if that's true, well then what we have is we always have single arrows going out here to other values over here. Okay, there's never double arrows because it is a function, if that makes sense. Okay, so guys, once again, this was Jonathan Lambert with the Mathematics Development and Support Service at the National College of Ireland. Okay, and I hope that this video, which was dealing with functions, and we took the approach of defining a function to be a restriction on a relation. Okay, I hope that this particular video was in some way intuitive, and more importantly, I actually hope that was helpful for you. We can probably leave this now, and we can actually concentrate on some applications of functions where we define functions and we define some sort of some operations like composition of functions, injective functions, surjective functions, and what's known as bijective functions. Okay, so once again, this is Jonathan Lambert with the Mathematics Development and Support Service at the National College of Ireland, and I hope that this video was in some way intuitive, and more importantly, I hope that was helpful for you, and thank you for watching.